Hello everyone. This is the mechanics of material. Uh, in this video, I'm going to show you how to calculate the internal force of a material and when applying an external load. Okay, this is a very common analysis method in mechanics of materials, so you must learn it. Okay. And as we keep saying that the mechanics of material is a study of the internal effect of stress and strain in a solid body that is subject to external loading. Okay, so a material, a rich body material is there. We apply a load on this material, and then the material itself will generate the internal stress and strain to respond to the external loading. Okay, and there's some very some force. Okay, this is a classification of the internal force. We have the normal force, shear force. Okay, normal force and shear force, and bending moment and torsional moment. Okay, when you apply external loading to your material is in the material, and the material itself will generate normal force, shear force, and torsional moment or bending moment to respond to external loading. And previously, we have demonstrated a very simple demonstration on what the normal force is, what the shear force is, and what the bending moment is, and what the torsional moment is. Okay, let's give you a physical idea what these forces and moments are. Okay, and now we have to learn to calculate these internal forces or moment applying an external loading. Okay. And yeah, we start from the example 7.1. Okay, this is a beam. Okay, this is a beam and it's a fixed support. Yeah, the problem did not say it's fixed support, but I think this problem should say this, should tell you this. Okay, this is a beam of this beam is here, and A here is a fixed support. Okay, this is a fixed support. And this being, we apply an external loading, and it's a distributed loading. I apply a distributed loading, and then the problem won't ask you about what is the internal force at this section, at this C section. What's the internal force at this C section? Okay, yeah, just calculate what the internal force is. Okay, and this is a very typical analysis in mechanics of material. For this problem, you want to calculate internal forces. Okay, we use a cut section method. Okay, cut section method. Okay, but this means because the problem we want to calculate the internal force at this C point, so we cut the section here. Okay, we cut a section here. Okay, but when you cut a section, it will create a problem. Okay, let me draw this picture. Okay, you will have a problem. Okay, you will cut a section as C. Okay, you have this situation. Okay, I cut a section as C, and this is B, and we cut a section. So actually you can imagine we split this bit in two parts. Okay, to cut this section. So actually, you split these two parts, split this being in two parts, and okay, and this tell you what I want to say. Say this because you cut this section, you can calculate BC section, and you can also calculate AC section. You have two ways to analyze this problem. You cut a section C, cut a section here, C here. You can do the analysis at CB section and the other, or you can do analysis on AC section. No matter which section you are going to analysis, you will have the same answers. You will have the same answer. You will have the same answer. So okay, so the next problem is okay. Yeah, if this problem is no, if the problem is correctly is okay. Sorry, if the problem is there's no if the number of this problem is all set up, no matter you calculate in AC section or BC section, you will give the same answer. You finally you will have the same answers. Okay, so the next problem is, okay, which way you will have a much easier calculation. Okay, so for in this problem, I think using the CB section is much easier to do the calculation. Okay, why? Because, okay, let me address another important point for this in this analysis method. If you calculate CB here, that means you ignore everything. Yeah, I think you should not. If you use the CCB section, okay, ignore everything in AC section. Okay, if you choose AC section to analysis, you can ignore everything in CB section. Okay. Okay, that's the thing you have to remember. If we use a cut section method, okay, if you use a CB section, ignore everything on the AC. Okay, if you use AC section, ignore everything in the CB section. Okay, okay. So okay, for this problem, why did I say why I say, okay, using the CB section is much easier to do the calculation. That is because, okay, at the very beginning, I say A is a fixed support, okay? And the fixed support, if you still remember the support reaction, the fixed support, it will create a reaction force AX and AY. And also because fixed support, it also has reaction moment. Okay, so if you use AC section to do the calculation, you need to calculate, okay, you need to calculate the reaction force at the A point. Sorry, that's wrong. If you use AC section to do the calculation, you have to calculate the reaction force at A and also a reaction moment at A. Okay, if you want to use AC section to do the analysis to calculate the internal force at the C section, you need to calculate reaction force, reaction moment from A. But if you use a CB section, yeah, you don't have to consider the reaction force and reaction moment from at the fixed support. So this will reduce the calculation burden reduce your calculation burden if you choose the CB section. But I have to say, no matter you use the CB section or AC section, your final result will be the same. Okay, the result is the internal force at C. No matter you use this one and use this one, you will get the same answer. Um, for this problem, I will demonstrate these two methods. Okay, I will do a demonstration calculate using the CB section and also using the AC section. I will do both. Okay, but in this video, I will use the CB section first. Okay, in the next video, I will use the AC section. Okay. Okay, let's start from the CB section. Okay, using the CB section. So for the CB section, okay, we can ignore the reaction from the supports. Okay, so we can just delete it. Okay, in next video, I'll demonstrate how to use the AC section to calculate. Okay. Okay, so we focus on the CB section. Okay, for the CB section, okay, let me draw the picture one more time. If you use the CB section to do the calculation, okay, CB section, the CB section here, okay, and we still have distributed load in here, okay, we still have distributed load in here. Okay, and this section as you use the zigzag. Okay. Okay, here the first of all, if you cut the sections, either this C section. Okay, the first thing. Okay, what is the distributed load here? What is distributed load here? What is the distributed load here? Right here. Okay, at least A end, it's 300 Newton per meter. That's at least A end. But what I'm asking now is, what is the magnitude here at this C point? Okay, at this C section. At A is 300, but what is here? Okay, what's the force intensity here? Okay, so how to calculate force intensity here? Yeah, I think in a very short time you may want you may feel very confused how to calculate the value here. Okay, so let's draw another picture here. Okay, I think every one of you can understand this. Okay, let me. Okay, okay. Okay, origin is 300. This is 0. Okay, this is 3.6, right? 1.2 plus 2.4. And we have section C is here. And here it says 1.2. And so here is 300. And so what is this? Okay, what is magnitude here? Okay, so how to calculate the magnitude here? Remember that? Okay, similar triangle, right? Okay, this is 2, this is 1.2 here. That means this is 2.4. So 2.4 over 3.6 equal to the question mark over 300, right? Similar triangle, right? Remember similar triangle. Okay, don't forget this. This will use. Okay, this used a lot in mechanics engineering calculation. Okay, in a yeah, mechanics or mechanics of material calculation. Okay, so what is the question mark? So this is 3, 2. So the question mark is 200. Okay, so here is 200. It's 200 Newton per meter. Okay, that's the first thing you have to know. If you cut a section as C here, okay, you need to know the magnitude here. So 200 Newton per meter. Okay, next thing is, okay, in the section C, what force do we have? Okay, typically the internal force, we have the normal force. We have normal force and also the shear force. Okay, the symbol for the shear force is V I think in this textbook. And normal force at C. Also, we also have a moment at the C. Okay, also a moment at C, right? Okay, so the question is, what is VC? What is NC? What is MC? Okay. Okay, so how to calculate this? Okay, don't forget, in this course, everything is statics. In this course, everything is statics. Statics. Okay, what statics mean? All total force equal to 0, or total moment equal to 0. Okay, because in this course everything is static. So it's static, that means you reach body equilibrium, and then reach body equilibrium means the resultant force is 0 and the resultant moment is 0, and the whole system yet is statics. So we have to use the rigid body equilibrium to find out the BC, NC, and MC. Okay, so and the next question is, okay, so this is distributing loaded here, okay, and we need to do the simplification of distributed loading, okay, simplification of distributed loaded, okay. So how to make how to do the simplification of this distributed loading, okay. I hope you don't forget this. Okay, so we need to do a simplification, okay. Simplification. Yeah, this problem takes a time. Okay, so let's draw it again. Okay, this is B, this is C here, and we'll know. Okay, simplification. Okay, what will simplification do? Run simplification of distributed load. We need to find FR, right? FR and the position of the FR, right? Okay, what is FR? FR is the area under the distributed curve. okay, under this distributed curve. Okay, so that's why the force intensity at this C point is very important, because this will help you to calculate area under this curve. Okay, so this is a right triangle. So what's the area of this right triangle? Okay, 1/2 times 200. And what is the length here? Okay, don't forget this is 2.4, 2.4. So that's your resultant force. Okay, so it's 240 and it's Newton. Okay, and what's the position of the resultant force? Okay, position resultant force. This is a right triangle. This is a right triangle. So don't forget the conclusion. Okay, this distance must be. This distance must be. You remember that? This distance must be 2.4/3, so it's 0.8. Okay, so this is 0.8. So here is 1.6. Okay, this is 0.8. Okay, because don't forget the centroid of the right triangle. Yeah, centroid of right triangle. I don't want to explain this anymore. You should memorize this or take a note of this. Okay, it's very important. This used a lot. Okay, this is right. The position just the centroid of the area. Okay, centroid area. So it's 2.4 divided by 3. Okay, so we have resultant force and position resultant force. I think, okay, don't forget what we have: normal force, shear force, and moment as C. Okay, so with all this information, I think we can solve everything here. Okay, so okay, so let's erase something here. Okay, let's start from this. Well, let's reuse the rigid body equilibrium. Okay, rigid body equilibrium. Resultant force is 0, resultant moment is 0. Okay, and this is a 2D problem. So, summation f of x equal to 0. So let's see, do we have x component force? X component, we don't have, we only have the normal force. Sorry, this should be VC. Okay, so we only have, what do we have? X component, we only have NC is X component and it's point to the left. It's point to the left. So minus NC. Okay, and do we have other X component force? No, equal to 0. So NC is 0, normal force is 0. Okay, we got one, easy, right? And sigma Fy equal to 0. Okay, the resultant force, Y component resultant force also 0 because everything is static. Okay, let's see the Y component. We only have a VC point up. Okay, VC point up, positive. And the resultant force here is Fr point down. And resultant force is 240 Newton, but it's point down. So it's minus 240. Okay, it's 0. Okay, do we have anything else? No. Okay, so VC is equal to 240 Newton. And finally, what's the moment at the C? Okay, here I should say MC. How to calculate this moment at C? Okay, let's see. Okay. The total moment must be 0. Okay, total moment must be 0. Okay, NC here, we don't know its direction. Let's assume it's counterclockwise. MC of summation M. Okay, MC. And do we have any, I think this two force won't create a moment at this C point, but C point here, it has an internal moment. Okay, so we still have to count it. See, this section has internal moment, so you have to MC here. Okay, and VC and C won't create a moment at this C section, but FR will create a moment. FR is here, point down, its labor arm is 0.8, so it's FR times 0.8. If the reference point is C, so it will generate a clockwise rotation, clockwise. For FR is pointing down in a clockwise rotation, so it's a negative equal to 0. Okay, MC and minus FR is 2.2. FR is 240 Newton times 0.8 is equal to 0. Okay, so finally the MC, what is MC? MC is 192 Newton times meter. Okay, right now we have an issue here. Okay, MC is here we got a positive value. Okay, but at the beginning I assume it's positive because counterclockwise rotation and this is clockwise rotation. Yeah, but the answer is minus sign. Okay, let me check what's going on here. Okay, okay, this answer is correct. Okay, this is correct. Okay, this is correct. Okay, okay, and the PowerPoint, the answer in the PowerPoint is minus 192 Newton times per meter. That's because I'm not sure. I think in textbook it's assume MC is assume. Okay, here the answer is assume MC is clockwise. Okay, it assume MC is clockwise, so you get a negative value. That means it's counterclockwise, right? But right now in my demonstration, in the beginning I already assume it's counterclockwise, so that's why I get 192 Newton times meter. For the PowerPoint answer, because I'm not sure in textbooks, it assumes it's clockwise. Initially, it assumes it's clockwise. And then the answer is minus 192 Newton times per meter. The answer is negative sign. That means it's reversed to your initial assumption. So the answer is still counterclockwise. So this answer is the correct. It's counterclockwise. Okay. Okay, so at this section, we have normal force 0, okay, and the shear force 240 Newton point up, and also at this C section we have a counterclockwise moment 192 Newton times meter. Okay, so we use the CB section to get these answers. Okay, in the next video, I will show you that if we use the AC section to do the same calculation, you will have the same answers. And you will understand if you use the AC section to do the calculation, the calculation will take much more longer. Okay, not only because of the reaction force issue, but also if you use the AC section to do the calculation, the distributing loaded will become a trapezoid. Okay, that will make the whole calculation much harder. Okay, but you will still get the same answer as using CB section. Okay, you have the same answer, but I will demonstrate in the next video. Okay, see you in the next video. I'll just stop video here. Okay, bye bye. Okay.